In this lesson, we're going to focus strictly on vertical stretch or shrink. So we're just going to look at this for right now, and then in the next lesson, we're going to look at horizontal stretch or shrink. But this is just going to be focusing strictly on vertical stretch or shrink, and this is part 2 of our study on vertical stretch and shrink. And in particular, in this lesson, we're going to be interested in finding the rule for transformation, the transformation rule for vertical stretch or shrink. And remember, another word for shrink is compression. Now, we got to remember something about the previous lesson that we did. So we saw in the previous lesson that if we have a we have a vertical stretch or shrink, we have this situation where we have y equals c times f of x. All right, so we have that situation. So when you have that, that's considered a vertical stretch or shrink, depending on what c is. So we saw that if c is greater than 1, then we have a vertical stretch. Now, what that meant was if you go back to your example where we had in the previous lesson, so f of x was x squared, so that's that blue graph, and then we want to graph h of x, which was 2 times f of x. So c here was 2. So since c is greater than 1, remember what happened. So every point, so see, look at this. So every point on the graph of f of x, all right, the y value doubled. So you see this y value was 4. When I doubled it became 2. So it became that point. So notice the x value stayed the same, but the y value doubled. So if I go here to this point where on the blue graph that was the y value is 1, when I double it, it became 2. Okay? So you had what was being involved. So whenever c gets bigger and bigger and bigger, your graph becomes more narrower. So it kind of goes towards the y-axis. All right, and then we saw that if c was less than 1, like 1/2, but still positive, it became kind of bigger, so to speak. All right, so it moved away from the y-axis towards the x-axis. All right, so that's what we talked about in part 1. So if c is greater than 1, we have a vertical stretch. And then we saw that if c is less than 1 but still positive, we have a vertical compression or shrink. Okay? Now, in this case, though, we want to determine, well, how do I go if I'm giving a point on f of x and I want to transform it, then how do I do that if I'm given a point? What's the rule? All right, so that's what we're trying to find, this rule. What's the transformation rule? Okay? All right, so what we're going to do is kind of go back and forth to our previous lesson where we had these graphs. All right, so we're going to go back and forth to that. So you'll notice that when we graphed f of x, right here, I use these x values, okay? And we use these x values to help us to get these other graphs, and still having a discussion about what does c do to it, to the graph of f of x. So what I want to do here is this. So we know that when I graphed f of x, which remember was x squared, okay, I should have put that here, f of x, which equals x squared. I got a y value of 16, because negative 4 squared 16, which gave me a point, which became the point negative 4, 16. Okay? When x was negative 3, I got 9, which gave me the point negative 3, 9. That's what I plotted. So remember right here? So negative 3, 9 was right here. All right, so that's what we were doing. When x is negative 2, I got the point negative 2, 4 on the graph. When x is negative 1, I got the point negative 1, 1. All right, so all I'm doing right now is just labeling these coordinates. So I'm taking all these points here that we plotted, and I'm writing them as an ordered pair. All right, and so here we have 1, 1, and then 2, 4, and then 3, 9, and then 4, 16. All right. Now, what we did next was we looked at h of x. All right, so h of x, remember, was this. Was 2x squared, which, remember, was the same thing as saying 2 times f of x. So c here was 2. And so then we saw that negative 4, when I plugged in negative 4, I got a y value of 32. So I got the point negative 4, 32. And then so on. So if you keep doing this, you'll see what I'm getting at. So this was 18. So remember what happened was that this 2 doubled these y values. Remember that? 16 doubled, 9 doubled. That's what's happening. So you're taking the y value here of f of x and you're multiplying it by 2. Okay? But we got negative 3, 18. So when I double 4, remember I got 8. So I'm getting the point negative 2, 8. That's the point I would get on h of x. So if I go back, you'll see that negative 2, 8 is on negative 2, 8 is on h of x. Okay? And continue on and so on. Okay? I'm not going to do all of them because I'm just trying to come up with a rule. So if I go to the next one, which was k of x, 1/2 x squared. So k of x, which equals to 1/2 x squared, which is the same thing as 1/2 f of x. So notice this time c was 1/2, so that's where we had that vertical compression. All right, that vertical compression. So we're pulling it away from the y-axis. And so when I do the same thing here, remember what happened there. So when this says that if my y value is 16, I'm taking half of that, so I got what? 8, right? So I got the point negative 4, 8. And so if I go to my graph and I look at negative 4, 8, that is right here. So remember the point negative, on this graph it was negative 4, 16. It became the point negative 4, 8. Okay? So what's happening is that the values decrease. So that's the idea of shrinking or compressing. So you're compressing this graph. To get this graph, you're compressing this graph. So the point, notice the x values stay the same, but the y value becomes smaller. So it's compressing. All right, so here, this became, so when x was negative 3, this became 9/2. So we had the point negative 3, 9/2. Here, when x was negative 2, the y value in f of x was 4, and this became, for k of x, it became 2. So we got the point negative 2, 2. All right. So and then you can go on with this. But the point's this, though. So let's look at this rule. So what do you notice about in all these points? What do you notice about the x-coordinates? The x-coordinates stay the same, right? What changed, though? The y-coordinates. The y-coordinates. And so it changed by this idea. So look here. So remember, this is f of x. So do y'all agree that to get 32 here, I had to take 16 multiplied by 2, right? So 2 times 16 gave me 32, correct? Over here, to get at 18, I had to say 2 times 9. Y'all agree? So 2 times 9. To get 8, I had to say 2 times what? 2 times 4. Okay? Same thing here. To get 8 here, I had to say 1/2 times what? 16. To get 9/2, I had to say what? 9 times 1/2. So I want you to think of the rule. So the rule is that if on my function f of x, I have the point xy, it becomes what point? Well, remember, what stayed the same? The x value stayed the same in every case, didn't it? So the x value is going to stay the same, but what changes? Y. And how does it change? Well, all I did was I took this y value, multiplied it by c. 16 times 2 is 32. C here was 1/2. 16 times 1/2 is 8. So all you do is take your y value, multiply by c, and there's your rule. Okay? So the rule for a vertical stretch or shrink is this. So the rule, your transformation rule, is this. So a point on your function becomes, with the transformation, whatever the transformation is, becomes x c times y, whatever c is. All right, so that's your rule. Okay? All right, so let's look at an example. Okay, so the example I want to use is this. So we're going to use an example. So here's my diagram. Okay, here's my graph, and it's made up of segments. Okay, and notice I have a horizontal segment here because I want to talk about that at some point. So notice that all these other segments are slanted. They have some kind of slope other than 0. All right, so they're slanted. So we're going to have the discussion when we do these transformations. All right, but there's my function f of x. All right, so what I want to do in number 1 is this. I want to graph g of x, which equals, let's say, 2 times f of x. All right, so let's graph g of x, which equals 2 times f of x. All right, now as we talk about that, we're going to look at these points. And the way we're going to graph these, since these are segments, it's kind of easy to deal with. We're going to look at each point. We can look at each of those endpoints. So here, I have to see, I'll agree that this point here is negative 6, 4. Negative 6, 4. So negative, so remember this is f of x right here. So a point on f of x is negative 6, 4. It becomes what point on g of x? That's the question. Well, remember, my rule says the x value stays the same. So remember, this is a vertical. You agree that that's a vertical stretch, right? Vertical stretch. So basically what's happening is that since that's a vertical stretch, the segments are going to get longer. You're going to see it's going to be stretched. All right. So you're going to see this idea is going to get bigger. So this is going to get bigger. Now we're going to see what happens here because that's horizontal. How do you vertically stretch a horizontal segment? All right. So that's going to be a discussion. Okay. Now, how do you vertically stretch a horizontal segment? Okay, so negative 6, 4 becomes, remember the x values stay the same. Because remember we're taking this point and we're moving it up. We're taking this point and we're moving it down. All right, so those points, the x value stays the same. It's the y value that changes. So we're moving it down. So that x value stays the same as the y value that changes, right? Okay, so you see like this. Okay, so the point negative 6, 4 becomes the point negative 6, and all I do is I take my y value, multiply by 2, so I get 8. All right, because we said 4 times 2, 4 times c. C is 2 in this case. All right, so c is 2. All right, so I'm going to plot that point. I'm going to use a red color here. So negative 6, 8. So I'm going to plot the point negative 6, 8. That is here. Okay. So then let's go to the next point. So the next point we look at is this one here. So that's negative 4, negative 3. So negative 4, negative 3 becomes what point? Well, negative 4, and we multiply negative 3 by 2. So negative 3 times 2 is negative 6. So I'm plot the point negative 4, negative 6. So that's here. And so you see what happens to that segment? So it got bigger, didn't it? So I stretched it. I stretched that segment. I stretched it. So it's a vertical stretch. Okay? Vertical stretch. Now let's look at this point here. Remember, that's the horizontal one, right? So I want you to think about this. Remember, the x values stay the same. So if the x values are the same, then it's still going to be that same distance, right? Because you really can't vertically stretch a horizontal segment. So the x values stay the same. It was the y values that's going to change. So the y values are changing. All right. So this is the point 1, negative 3. So 1, negative 3 becomes the point 1, and we double the y value because c is 2, negative 6, doesn't it? So 1, negative 6, which is right here. All right, so notice that whenever you have a vertical stretch and even a vertical shrink, the horizontal segments will be the same length. Let's look at the next point. So the next point here is 4, 2. So 4, 2 becomes 4, double 2, 4, 4. So 4, 4 is here. All right, so this point, I'm moving it up because remember this is a vertical stretch. All right, and then okay, so then I'm going to connect those, and I want you to think about this. So you see the distance here from the x-axis is 2 units, right? And so now, since I multiply the y value by 2, now how many units? 4. So that kind of makes sense. That I'm doubling this thing. So that's going to be what here? Okay, and then the point 6, negative 1 becomes the point 6, negative 2. So when I plot the point 6, negative 2, I get this. All right, so remember, you're taking each point and you're moving it away from the x-axis. All right, so vertical stretch, you're moving it away from the x-axis. Vertical stretch, you're moving it away from the x-axis. Vertical shrink, you're moving it towards the x-axis. All right, so just keep that in mind. Okay, now, so we're going to connect those points. Okay, and so there's my graph. So it's still the same configuration, except it got larger. So I did a vertical stretch. So my function f of x, g of x is larger by a factor of 2. All right, so it's larger by a factor of 2. Now let's look at this one. Let's suppose I want to graph number 2, h of x, which is 1/2 f of x. All right, 1/2 f of x. All right, so we're going to do the same thing. We use that same idea. So remember, since c is 1/2, that's going to be a vertical compression or a vertical shrink. All right, so you can see that I'm going to use the green color here, so you can see that my function f of x, I'm going to shrink it. Okay, I'm going to shrink the graph. All right, so we're going to do the same process. We're going to take a point on f of x, and we're going to ask ourselves, what does it become on h of x? So here's f of x. So my point was negative 6, 4. It became, for h of x, it's going to become what? So remember, c here is 1/2. So remember, the x value stayed the same. The y value changes. So I multiply the y value by 1/2. So 4 times 1/2 is 2. So I'm plot the point negative 6, 2. So negative 6, 2 is right here. And so basically it kind of makes sense because you're taking this point here and you're taking the y value and taking half of it. All right, so instead of the y value being 4 units, it's now 2 units. All right, so it kind of makes sense that's what happened. Over here, my y value is 3, right? Negative 3, so it becomes negative 1/2. Y'all agree? All right, so it kind of makes sense. So the point negative 4, negative 3 becomes the point negative 4, negative 3/2, which is negative 1/2. So I get this point right here. Negative 1/2, 3, negative 4, 1/2, negative 1/2, negative 4, negative 4, negative 1/2, which is here. All right, so I'm going to connect those two endpoints, and I get this. Okay, then let's look at the horizontal segment. So 1, negative 3 becomes 1, negative 3/2, right? So 1, -3/2 is right here. So again, the the um, the horizontal segment, the length of it stayed the same. Okay, the point 42 becomes a point 4. Take half of 2, you get 1. So it becomes a point 4, 1. Kind of made sense, because remember, this is a vertical shrink. All right, so you're taking this point here and you're moving it towards the x-axis. All right. So we get this right here. And so it's like this. All right. And then the point 6, -1 becomes a point 6 and the negative multiplied by 1/2, so 6 -1/2. So 6 -1/2. So 6 -1/2 is right here. Okay? And so the green graph is g of x. All right. So that's h of x, sorry. So this is h of x here. And the red graph was, I think we called it g of x. So the red was g of x. All right, so that's all you do. So that's how you use the rule to draw your graphs. So if the graph is given and you asked to transform it, then use points on the graph to use your rule with. Okay. All right. Let's look at another example with a vertical stretch or vertical compression. So just remember though, before we do that next problem, just remember that the when you're dealing with a vertical stretch or compression, it's the y value that changes. So either you're going away from the x-axis or you're going towards the x-axis. Okay? All right, so just keep that in mind. And over here, you remember the diagram stays the same. It's just that the shape either becomes smaller or larger. So that's why the horizontal segments stay the same, because you're still dealing with that same diagram. So a horizontal segment will stay horizontal. Okay? All right, now let's look at this example. So in this example, you're given that f of x is x cubed. So that's going to be our parent function. And we're going to graph g of x, which is 2x cubed. And you want to use our transformation rule to do that. Okay, so first of all, let's look at what x cubed looks like. All right, so here's x cubed. All right, so x cubed, we're going to plot some points. And so when x is 0, 0 cubed is 0. When x is 1, 1 times itself 3 times is 1. When x is 2, 2 cubed is 8. All right, and then let's do -1. -1, I get -1 cubed is -1 times -1 times -1, which is -1. And when x is -2, I get -2 times itself 3 times is -8. And so what happens is this. So I get this graph, so I have 0, 0. I have 1, 1, and I have 2, 8, way up here. And then if x was 3, I would get 3 cubed. If x is 3, I get 3 cubed, which is 27. And I didn't do that because I didn't have enough space. So the graph kind of looks like this. All right, so here's a graph of x cubed. And then this side, -1, -1, and the -2, -8 is here. All right. Okay. So there's the graph of x cubed. So it looks like this. Okay. All right. So what I want to do though is I want to graph. Remember, this is f of x. So I want to use transformations to graph g of x. All right. So I use transformations to graph g of x. So remember our transformation rule. So first of all, you got to remember this is a vertical. This is a vertical stretching, right? Vertical stretching. So this is a vertical stretch. And so the rule says I take the point that's on here, and to get the new point, I'm going to multiply the y value by c. That's the rule. And so c in this case is 2. C in this case is 2, because remember, g of x means the same thing as saying 2 times, and this is f of x. All right, so this is f of x, and I want to graph 2 times f of x. I'm going to have to use these transformation rules. So the point 0, 0 becomes what point? So I take the y value, multiply by 2. Well, the y value is 0. 0 times 2 is still 0. So the point 0, 0 stays 0, 0. The point 1, 1 becomes what point? So remember, the x value stay the same is the y value that changes. So I got to multiply the y value by 2, which is 2. So the point 1, 1 becomes the point 1, 2. All right. Now the point 2, 8 becomes the point 2, 16, right? 2, 16. So again, I don't have enough room, so that's going to be way up here. But the point being that on this side, I get something that looks like this. Okay, something looks like that. So remember, that's a vertical stretch. So the graph, remember, the graph becomes more narrower the bigger c gets. And over here, if I do the next one, the point -1, -1 becomes what point? Well, it becomes the point -1, -2. So I multiply the y value by c, which is 2. -1 times 2 is -2. So -1, -2 is this right here. Okay? And then again, if I do -2, -8, it becomes the point -2, -16. So that's way down here, -2, -16. So I get this now. And so that, the red graph would be g of x, which is 2x cubed, which means 2 times f of x. All right? So that is how you can transform x cubed. Okay? Now that's a little bit harder to do because you're cubing, so those y values get bigger and you may not have enough room. So that's why it's a little bit more difficult to do x cubed, to transform x cubed. All right, now let's go to the next example. Okay, so in this example, you want to graph g of x, which is 2 times the absolute value of x, and you use transformations. All right, so you don't want to use a t-table to graph this. You want to use transformations. Okay, so you got to remember, I can write this as g of x, which equals 2 times f of x, where f of x is the absolute value of x. Okay, so given the absolute value of x, remember the absolute value of x looks like this. That's the shape of a V, so that's f of x. And so notice that on f of x, right here, I have the points 2, 2, 4, 4, and so on. 1, 1, 2, 2. So remember, the absolute value of x, so when x is -4, when x is -4, my y value is +4. When x is -8, my y value is +8. All right? So all these points you talked about in the previous lesson still apply here. That's the graph of f of x, which is the absolute value of x. What I want to do, though, is graph g of x, which is 2 times the absolute value of x. So remember, you got to think like this. So you know you can write this as 2 times f of x, where f of x is the absolute value of x. So this is a vertical stretch. That's a vertical stretch. Okay? So let's see what happens. So the point, so remember this is a point in f of x. So f of x, let's look at the point. So the vertex here is 0, 0. For g of x, it becomes what point? So remember, you're vertically stretching. So every point here, you're going to move away from the x-axis. You're moving it away from the x-axis. Is that clear? All right? So if you had one down here, you move it further down, away from the x-axis. But all my points here are either on the x-axis or above. So it's going to move away from the x-axis. Now, if it's on the x-axis, it stays there. Okay, it's going to stay there. Okay, So the point 0, 0, remember our rule is that xy becomes x times x comma cy. So c in this case is 2. So c is 2. All right, so I multiply my y value by 2. So the point 0, 0 stays 0, 0. All right, so that's going to be the green graph. All right, so then the point, let's say 2, 2, right here, 2, 2 becomes what? 2, 4, right? Because 2 times 2, the y value, c is 2, so 2 times 2 is 4. So I get the point 2, 4, which is here. So you see how this point's moving away? I'm moving it away from the x-axis. I'm stretching it. So it's going to become narrower. Becomes narrower. Okay? The point 4, 4 becomes 4, 8. So 4, 8. So I get this. And you can continue on, but you don't need to do all this. So, because these are rays. And so over here, negative 4, 4, what do you think that becomes? So negative 4, 4 becomes the point negative 4, 8, right? So negative 4, 8. And so if I graph this, I have enough to graph this v. If I have this, you see it became narrower. That was our discussion in part 1. So we get this. All right. So I use, now to get g of x, I use the idea of transformations. In this case, it was a vertical stretch. All right, so that is, you see, I'm moving it. So when you do a vertical stretch, you're kind of moving it towards the y-axis. So you're taking your points away from the x-axis and kind of moving the graph towards the y-axis. So you're doing a vertical stretch, which makes it look skinnier. It makes this graph look skinnier. So the bigger C is, the skinnier this thing gets. Okay? Now, let's do the next one. So still using this, let's look at part B. Suppose part B, I had h of x, which is 1/2 absolute value of x. All right? So remember, this is absolute value of x right here. So what do you think this 1/2 is going to do to it, to this black graph, to this f of x? So is this a vertical stretch or a vertical shrink? Do you think it's going to go towards the y-axis or away from the y-axis? It'll go away. All right, so it'll go away. So this is going to be vertical compression. All right, and help yourself by doing this, by saying this is the same thing as saying h of x equals 1/2 f of x, where f of x is absolute value of x. So it does help to think in terms of something like that. All right, so we're going to do the same thing. So we're using transformation. So the point 0, 0, remember this is f of x, and we're going to transform it to h of x. So the point 0, 0 becomes what point on h of x? Becomes a point 0, 0, because remember c here is 1/2, right? And so our rule says the point, whenever I have a vertical transformation, either stretch or a shrink, the rule is that the x value stays the same. I got to take the y value multiplied by c. So 0 times 1/2 is still 0. All right, so I'm going to use the red graph for that one. So I get 0, 0. The point 2, 2 becomes what point? See, I'm still using the same points here on f of x. The point 2, 2 becomes 2 what? What's 2 times 1/2? 1. So I plot the point 2, 1, which is here. Okay? The point, let's say, 4, 4 right here. Remember, basically what's happening is, since this is a vertical compression, I'm moving it towards the x-axis. So I'm taking every point, I'm moving it towards the x-axis. So I'm compressing this. So the x value stays the same, but the y value gets smaller, right? I'm moving it towards the x-axis. That's what's happening. All right, so 4, 4 becomes the point 4, 2. So 4, 4 becomes the point 4, 2. So 4, 2 is here. And then you continue on if you want to. So 8, 8 becomes 8, 4, right? 10, 10 becomes 10, 5, and so on. Okay? On this side, same thing. Negative 4, 4, let's say. Negative 4, 4 becomes what point? Negative 4, half of the y value is 2. All right? So that's your vertical compression. So you see how you're moving it towards the x-axis? So that's called a vertical shrink, though. All right, so it's a vertical shrink. So vertical stretch is where you're moving it towards the y-axis, which makes it look like you're stretching f of x. All right, so and a vertical compression, a vertical shrink, is you're moving it away from the y-axis towards taking every point, moving it towards the x-axis. Okay. All right. So that is this one was we call this h of x. So this is h of x here, and the green one was g of x. All right. So the takeaway from this one is this. So whenever you're dealing with a vertical stretch, you're taking the point on your basic function, in this case f of x, when you're dealing with a vertical stretch, and you're moving it away from the x-axis. Okay, you're moving it up, which basically means you're taking the whole graph and moving it towards the y-axis. When you have a vertical compression, you're taking the point here, the y value, you're moving it down. You're taking this point, moving it down, which means that the y value changes. So the y value becomes smaller. So you have a vertical compression, a vertical shrink. So meaning that the y values are shrinking. So you're getting closer and closer to the x-axis. All right. So that is our discussion on how to use the rule for vertical transformations. And so the rule, remember, is this. So if you have a vertical stretch or shrink, then the rule is that you're going to take the point xy that's on the graph you want to transform, and it becomes x, and then the y value is going to be c times y. All right, so the x values stay the same. The y value, to get the new y value, you multiply the y value by c. Okay, so that is our discussion on vertical stretch shrink. The next one is going to be on horizontal stretch shrink. I'm going to come up with a rule for that one.